Okay, it's about 10:04 and that's our cue to get started. Unlike normally during the term, we can do this whenever we want. You can watch this whenever you want, and I can record them whenever I want. So as long as we get done with the semester. So this is Chem 230. And what we're going to move into now is some other types of isomerism. So we had looked at constitutional isomers of alkanes, and then constitutional geometric and conformational isomers of cycloalkanes. And we looked at conformational isomers of alkanes. Now we're going to get into some alkenes. And the difference between an alkane and an alkene is alkane with the ane ending has just single bonds, but alkenes have double bonds. And just for the record, we're not going to get into the E and Z nomenclature. That's a more modern nomenclature where you have to assign priority groups and everything, and for an introduction we're not going to get there. So right now we're going to look at cis-trans isomerism for alkenes, and this is going to be fairly basic. So if you understood cis and trans isomers for cycloalkanes, such as dichlorocyclohexane, then you should be good here. Geometric isomers of alkenes, compounds with the same formula, so all isomers are going to have the same formula and the same atom connections, can still be different and have different compounds. Similar to the situation with cycloalkanes, this can happen when different substituents have different relative orientations. Again, this would be relative to a double bond. So before, our frame of reference was the plane of the ring for ring systems. Now we're going to be looking at the axis of the double bond to orient whether things are cis or trans. So two substances will be on the same side, which is cis, or opposite sides, which is trans, of the double bond. Since there is no rotation about the double bond, the substituents can't be changing places. And this is, in the common language, there's been a lot of hype about whether foods contain trans fats or not. Most people probably have no idea what a trans fat is, but they know they should avoid it because labels say so. But the trans fats are ones where the fatty acids contain double bonds in which there's a trans orientation about the double bond. So also with omega-3 fatty acids, omega-3 is reference to the chemical structure of the fatty acid. And if you really want to know about nutrition, you should probably get into the chemical structure of different nutrients and trying to understand why something would be good or bad for you. When I mentioned free rotation, if we go back to butane, which has just single bonds, now these substituents look like they're across from each other, but because at room temperature there's enough energy to rotate about a single bond, they can be next to each other, then across from each other, then next to each other, then across from each other. They can pretty much rotate freely and change relative orientations. What this slide is saying is that once you put a double bond in place, and the mechanical models, the molecular models, mechanically do exactly what they're supposed to in terms of this topic. Now if we have a double bond in place, which I constructed, I can't rotate about that double bond. It's got 2 points of connection there and that locks it in place. So now if two things are across from each other, they stay across from each other. So the language is pretty straightforward. Relative to the axis of the double bond, two hydrogens are either going to be across from each other or next to each other. So in this is a butene, 1, 2, 3, 4 carbons, means the but root. The double bond means the ene suffix, and then we have to say where the double bond is starting. So if we number the carbons, 1, 2, 3, 4, then the double bond starts on carbon number 2, so this is 2-butene. And since with 2-butene, the two hydrogens that are on adjacent carbons in the double bond are either going to be next to each other or across from each other, we have to label that as well as the geometric isomer. So in this case, this hydrogen is on bottom side of the double bond, this hydrogen is on the top side, this would be trans. So here's trans 2-butene. And the other model that I built here looks different. Again, it's got a different shape. And unlike the butane case, now if these two methyl groups are next to each other, they're going to stay next to each other. So there's no free rotation about the double bond. This compound, also 4 carbons, 1, 2, 3, 4, 4 carbons. So it's a but something. Double bond means it's a butene. But now, and also the location of the double bond is important. So carbon 1, 2, 3, 4. It's carbon 2 is where the double bond starts. And then now the two hydrogens that are on the adjacent carbons in the double bond are next to each other. So this would be cis 2-butene. So that's an isomer of butene that you can have that's a particular geometric isomer of 2-butene. So 2-butene can either be cis or trans. We've gone through that. Now when you talk about isomers of butene in general, we first look at constitutional possibilities, because just looking at the skeletal structure, you put 4 carbons in a row, although I went ahead and started with the Lewis structure kind of formulation where I put in what the atom labels are. If I go back to skeletal, like I said, I can put the double bond between the first 2 carbons. So this would be a 1-butene. And in this case, it doesn't make sense to talk about cis versus trans because there's only one way to construct the 1-butene. If I put the double bond in place and then fill the octets on the Lewis structure of all the carbons, then we come to the formula here. And notice in this one, we have 2 hydrogens on the same side of the double bond. And there's 2 hydrogens on opposite sides of the double bond. So it doesn't make sense to talk about this as being cis or trans when it's sort of got both. So since on the first carbon there's 2 hydrogens rather than a hydrogen in an alkyl group, then there's going to be a hydrogen both next to and across from the other hydrogen. So this one, there's no geometric isomers. When you build it, it's going to be this molecule, right? Just neither cis nor trans for 1-butene. When you go to 2-butene, those are the ones that I built. That's where it gets a little more interesting maybe, because you can draw typical zigzag, and now relative to the double bond, the methyls are on opposite sides, the hydrogens are on opposite sides. So this is the trans 2-butene. But then you can draw the other one, where now the 2 hydrogens are next to each other. So this would be the cis 2-butene. And notice some people would go ahead and try to go 3-butene. But if you start the double bond on the 3rd carbon, it's really starting on the 1st carbon from the other side. So not a new isomer over here. The isomers of butene are going to be 1-butene, constitutional isomer with no geometric isomers, and then 2-butene is the other constitutional isomer. And remember, just like the cyclohexane substituents, the number identifies which constitutional isomer we're talking about. So the constitutional isomer distinction is given by the number, and then the geometric isomers, if you have 2-butene, you can have one of 2 geometric isomers. So things get pretty complicated when you start looking at compounds with lots of carbons and with various degrees of unsaturation. Remember, we talked about degrees of unsaturation as being either rings or double bonds. And so if you have a double bond, it can be in different places. If you have rings, the substituents can be in different places. So this can get very confusing or very complicated. Not necessarily confusing if you understand things, but it can get very complicated very quickly if you look at lots of different isomers.